These are notes for section 4.4b, average value theorem, which we can think of as the mean value theorem for integrals. So let me just read through definition here. If our function is able to be integrated on the closed interval between a and b, then the average value of our function on the interval is, think of average value as the average height, is equal to f of c is equal to 1 over b minus a, definite integral of f of x dx from a to b. So this is essentially moving around the formula for area of a rectangle. Right? If we think of, if we know that area is equal to width times height, then we can move things around and say that our height is simply area divided by the width, or height is equal to 1 over width times area. Right? And the idea is that if we have an interval here, right? Let's say this the region between the endpoints, the curve, and the x-axis produces a certain area, a certain value for the area. Then it's possible. Okay, imagine that we wanted to create a rectangular box out of this area. Okay, so imagine this was we're able to push down on this, which will force us to go up. So imagine we're taking the shape and we're forcing it to fit into a rectangle. Okay, and the idea is if we can fit it into the size of a rectangle, then the height that we arrive at when we produce that rectangle will be the average height, the f of c. Okay, so there exists a rectangle such that the area of the rectangle is the same as the area under the curve. Okay. So again, since height times width is equal to area, then height is simply equal to area over width, which is provided here. Okay. Okay. Example 1: find the average value of f of x of our average value for our curve x squared plus 1 from the intervals from 2 to 5. So we go through the steps. We can find the area first. Right? And the area, well, we can just set everything up. Our area is represented by the definite integral of x squared plus 1 dx from 2 to 5. Okay? Divided by the width, same thing as saying 1 over 5 minus 2 is equal to the height. Okay? So we just go through our process here. Go through our integral rule that we know with power rule. So 1/3 is the coefficient that's produced by the width, and then we go through power rule x cubed over 3 plus x. Evaluate between our upper and lower bound. So plug 5 in for x, we get 125 over 3 plus 5. So this is f of b minus f of a. Plug 2 into the function, x cubed over 8 over 3 plus 2. Okay. And this comes out to be 126 over 3. And the multiplying by 1/3 is the same thing as dividing by the width, which gives us 14. So we know the average height is equal to 14. Okay. So now the second part, it says find the c value. So what the c value tells us is we know that the graph is going to cross 14 at some point, right? Because 14 is the average height. So it's asking, when is the graph going to what x value is the graph going to cross this y value of 14, which is the average height? So here in the diagram, let's say the average height, let's say f of c is equal to 14, so we want to find out when is the graph going to cross that 14. And when we solve for x, then we can find the location of where the graph is going to hit that average height. Okay, so the way we solve for c is we set our function, this x squared plus 1, okay, equal to the average height, 14. We want to find out for what x value is the graph going to hit the y value of 14. So solve for c, subtract 1 from both sides, take square root of both sides. C is equal to square root of 13 because negative square root of 13 is outside of our interval. Okay, so square root of 13 is between 2 and 5, so that's our square root between 2 and 5, so that's why it's our C value. Okay. All right, the next topic is second fundamental theorem of calculus, SFTC. So the first theorem of calculus is essentially we can find the area under the curve by applying definite integral f of b minus f of a. So second theorem of calculus is really highlighting the fact that that integrals and derivatives are inverse operations of each other. Okay, so to recap, we've covered indefinite or general integrals, area finding functions. We've covered definite integrals, which is finding the area between two x values. Now there's also a function that is the integral itself. So let's say the function is defined by the definite integral of f of t from a to x. Okay. So instead of going from one constant to another constant, we are now going from a constant to a moving value of x. So what's representative of this integral function is, let's say we have a left endpoint of a, but the right endpoint is a moving variable. Okay, so if we want to find the derivative of a function that has a b value that is moving, or a right endpoint that is moving, then we have a rule for that. Okay, and the second theorem of calculus says if I want to find the derivative of a definite integral of a function that goes from a constant to a variable, then we can use properties of derivatives and integrals to in a way to do a shortcut to cancel a lot of the operations out, because we know that essentially the derivative operation and integral operation has a way of undoing each other. Okay, so really when these cancel out, we're just left with f of t. Okay, however, because one of the bounds is a variable, that's going to affect a bit of how what this derivative or what this will end up giving us.